Okay, so this is part 3 of our introduction to pseudospectral methods, and we've been working through periodic functions with the Fourier pseudospectral method. And in the previous presentation, we found that we can represent our function u of x as this summation, a linear combination of these Fourier modes. So it turns out that this linear combination of Fourier modes is simply the inverse discrete Fourier transform, which is great. And its counterpart is the discrete Fourier transform. And we can compare these two so that to look for the symmetries between them. So one of them has a positive argument, e to the 2 pi ij over n, and the other one is negative. Here that we have Cn coefficients, and the discrete Fourier transform has uj. The sum here is from n is minus n over 2 plus 1 to n over 2, whereas the sum here is j is 0 to n minus 1. We have the same number of terms. Both of these have n terms in them. And then this discrete Fourier transform has this normalizing factor 1 over n that shows up. So we'll denote these as the u is the inverse Fourier transform of the coefficient c, and c is the Fourier transform of u, denoted by f and f inverse. We can think of these as these u's are our function in the physical space. So our function u is defined on a grid in the physical coordinate. But the Cn are the representation of u in the Fourier, in the spectral space, because they're the coefficients of the Fourier modes. So the Cn can be thought of as the magnitude of the Fourier waves at the different wave numbers represented by index n. And this little picture kind of visually illustrates that. So the physical space, we take a fast Fourier transform to get to the spectral space, and those spectral coefficients Cn, if we take the inverse fast Fourier transform, they bring us back to the physical space. So we can show that u is f inverse times f of u, or u is also f of u, f times f inverse of u. So let's do that. If we insert this equation in for Cn, then we get this thing. But before we do that, we recognize that the summation j, we don't want that to conflict with this j. So we're going to change the notation here to be big J instead of little j, so that it doesn't conflict with this, which is an index, not a summation variable. So when we do that, we have this equation here. We're going to change the order of the sums. And when we change that order, we're going to write uj 1 over n times this summation here, and we'll combine the two exponents. So we end up with a little j minus big J. And so we can look at this term in brackets, and when big J equals little j, this term is 0, and e to the 0 is 1, and you have n of those. So you've got n, which cancels with this n, and so we end up with just uj equals the sum of these j's. But we also have that when j is not equal to j, this term in brackets is 0. So that means that we recover the uj is just uj, because the only term in the sum that's non-zero is when little j equals big J, and when that happens, the brackets are equal to n, and that term cancels. So hence we recover it, and we can show pretty explicitly that these are inverses of each other. When j is not equal to j, this term in brackets is 0, is basically saying that the sum of all these points around the circle sum to 0. So you can see for this particular image that these two will cancel, and these points, they cancel out as well. So you can show that in various levels of detail if you like. Okay, so there's lots of variations. The DFT, IDFT shown in these blue equations aren't unique. Sometimes you'll see this normalizing factor in the IDFT. Sometimes you'll see the signs being swapped. Sometimes you'll see this 1 over n being replaced by 1 over root n on both of the terms so that they look more symmetric. And that can make things a little bit complicated. So I've just listed a couple of those here. You'll also see the range cycled. So not both explicitly in terms of the equations and also as a function that most FFT libraries provide that you can cycle the coefficients to correspond to these two different sums. So when I say cycle the coefficients, I mean n goes from minus n over 2 plus 1 to n over 2, but you can also write it from m is 0 to n minus 1. So in other words, as long as you have the same points, it doesn't really matter if you label them 0, 1, 2, 3, 4, 5, or if you label them, as we've done here, minus 2, minus 1, 0, 1, 2, 3. Both ways of labeling them are the same, but you're just going to have a different, the coefficients will be a little different. So you can show that if you look at these two sums, and here I'm showing the CNs and I'm calling these C hats. So if you write out all the terms of the sum for n is 6, then you can see the sum over n and the sum over m's. And here I'm writing theta is 2 pi I j over n, and then that multiplies the little n. So here it's theta times minus 2, theta minus 1, theta 0, etc. And these exponential terms are all points in the complex plane on the unit circle. And if we look at the points for the sum over n and the points for the sum over m, you can see that they're the same points. We've just labeled them a little bit differently. So when you have minus 2, minus 1, 0, those correspond to 4, 5, 0, 1, 2, 3. So you have a direct correspondence between these. And for the sums to be the same, you need the coefficients to multiply the corresponding points. And that means that C minus 2 is equal to C hat 4, and C minus 1 is C hat 5, and C0 is 0, and C1, 2, and 3 are C hat 1, 2, and 3. So you just have to be careful of that. And again, there's functions in the FFT libraries that'll shift the coefficients for you. Okay. For other points for other values of j, these points listed are for j is 1. When j is 2 or 3, etc., you have this figure that we saw in the previous video where the points kind of, you'll go positive and you'll go negative and positive around the circle, but you end up with the same points for different values j. So it still works out. Okay. Now, our goal is to use these to show that, to evaluate the derivatives using high-order derivatives. So to evaluate derivatives on the grid, we're going to denote those as just duj dx, which is the same as the derivative of the function evaluated at point j. Now there's truncation error associated with using just a finite number of basis functions, but otherwise the evaluation is exact up to machine precision, and this is great. It makes for really high order methods that are efficient. So let's show how to do it. So we take the derivative of the function. So u of x is the sum over the basis functions of cn 2 pi I n x over L. If we take the derivative of this, then we get simply the 2 pi I n over L comes down and multiplies the original. And so you might say that the Fourier modes are eigenfunctions of the differential operator, meaning you recover your original function multiplied by a constant. And so we see that directly here. And if we take a second derivative, then we do that again, and we get this squared with a negative sign because I times I is minus 1. And you can extend that to whatever order derivative you want. So you can see that the c is just the f of t of u, and then we multiply that by this factor, and then we take the if of t of the result. And so we can write that here as the array of derivatives on our grid, indicated by the bold u here, is just the inverse Fourier transform times 2 pi I n over L times fu, where this circle dot notation just means we're taking this vector n, this vector here, and multiplying it element-wise by the result of the f of t, or the discrete Fourier transform. And similarly, for a second derivative, it's just minus, it's the inverse fast Fourier transform times this squared times fu. So like in Python, for example, you just do array multiplication. You take this array literally times this array. And this is what your code is going to look like. To evaluate a derivative, you're going to write f of t of u times this quantity where we write n as an array. And similarly for a second derivative. So let's show this in a PDE. In a PDE, if we have some diffusive flux, a conservation law du dt is minus the divergence of a flux, where the flux is minus diffusivity times a gradient. Then we have df dx is f minus 1 2 pi I n over L times f of the flux, and the flux is minus the diffusivity, which could be a function of u, making the whole thing nonlinear, which is fine, it just shows up right with this multiplication, times this vector f inverse. Again, this whole quantity is just representing the derivative right there. Or of course you can insert f in here, and then you get this long nasty thing that you then evaluate. Okay, so let's do an example finally. So we have du, let's do the viscous-Burgers equation. It's interesting, lots of people use it. There's an exact solution. It's nonlinear, and it's representative of the kinds of flows that you see in fluid mechanics, for example. So it's a useful test case. So let's let the domain be 10, and we'll solve it for a time of 10. We're going to use a periodic initial condition. It's basically just like a cosine wave. And then our exact solution, found on Wikipedia, I think, is given as shown. And I evaluated this thing using SymPy to calculate the exact solution. And then the spectral solution is given as follows, where we can say we have u multiplied by, that's the derivative, plus nu, the viscosity, viscous term, times the second derivative. And the difference here is you've got this thing squared. And so, and literally the code is going to look a lot like this. So let's have a look at the code. We've made a function called Spectral, which will solve it. We tell it how many grid points we want. The domain, we have, we're using this nu here is this viscosity, 0.1, the runtime. We create the grid, dx is L over the number of points. Create the grid points, create our initial condition, and then we're going to solve this using the method of lines. So we're going to integrate it using ODE int, the built-in function. And ODE int wants the right-hand side, the rates. So this whole right-hand side is the rates. So we make a function for that. We get the number of points is the length of u. And we make the vector of n's. And so it goes from minus n over 2 plus 1 to n over 2. So basically it goes from 0 to n minus 1, and then we just shift it backwards so that it has the right range that we want. And then this is the whole right-hand side. So this line right here is this thing. Okay, so let's look at it. Minus u times if of t times 2 pi I n over L times f of t of u, 2 pi I n over L times f of t of u, and then we take the if of t of that, the IFFT of that times u. And now this thing's going to be, technically it's imaginary, but the imaginary parts are all basically machine zero. So to just get rid of those, and so that u is always real, we're just going to take the real part. And then we're going to subtract off the second term, which is this viscous term, which is this part, nu times IFFT times that squared times the FFT of u. Right there. So crazy, right? Look how simple this is. It fits on one line. You're doing a spectral method in one line. It's kind of sad how many, this is like the third video. This should be on like the first 2 minutes of the first video. Sorry about that. Sorry, not sorry, because we have, there's, you know, it's fast to code, but there's lots of little details to understand. And we don't want to just code the equation. We want to understand what's going on. Okay, so then we make the times that we want to store it at, and then we solve the problem, and then we plot it. So here's what that looks like. Here's the blue thing is our initial condition, and then after it's cycled on itself, it's a periodic domain, so it evolves on a periodic domain, and it creates this object. And you can see the exact solution is the red curve, and the spectral points are listed. And it's, I mean, visually you can't distinguish the difference between the two. It's great. Okay, so now let's, we can compare this to a finite difference solver. So here we've written a function for a finite difference code, and we're going to use upwind on the advection term, and well, we're going to use central difference on the diffusive term, but we're gonna look at upwind on the advection term or central difference on the advection term. So kind of doing two methods. So if you're upwind, then the advection term is upwind, but we use central difference for the viscosity. And if we're central difference, we still use central difference for the viscosity, but we also use central difference for the advection term. So the advection term being this one, and the diffusive term being this one. So we're going to use central difference for this always, but we're going to use central difference or upwind on that term. And here's what that code looks like. Again, it also fits basically in one line for either method. We're taking advantage of using array syntax here, and you can see the details for that. And then we can compare the two methods for different number of grid points. So here, the blue are the spectral method, and I'm looking at the average relative error over this whole red curve when you change the number of grid points. And so you can see that the spectral method has what's called, we're plotting these on log scales, the spectral method has what's called exponential convergence. Converges faster than any power of n. Whereas the finite difference methods are power law. And those power laws end up with a given slope of 1 for the upwind method, or slope of 2 for the central difference. But you can see that the spectral method basically bottoms out and hits the round-off plateau when you get about 80 points. After 80 points, it's just round off. Can't get any better. Whereas, and you can see your error is like 1e to the minus 10. Your average relative error is 1e to the minus 10. Whereas the second order central difference at that same point has an error closer to 1e to the minus 3, so you're like 7 orders of magnitude better, at least in terms of the total error. And the upwind has an error of only about a little less than 1%. I mean, a little less than, yeah, 1%. So for an error of 4e to the minus 6, that should be minus 6. The spectral method requires 13 times fewer grid points, 40 versus 512, than the finite difference central difference method. And these spectral methods, again, they give exponential convergence. So that's one of the reasons why they're used. They're a little more expensive to evaluate a derivative, but the accuracy allows you to have so many fewer grid points that it makes up for itself. And the cost of doing this will be, of doing a spectral method, will be order n log n. So even though these are matrix operations, which normally would cost order n squared to do a matrix multiplication and order n cubed to do a matrix inversion of a full matrix, the cost using an FFT is only n log n, so much cheaper. Okay, and so that's where we'll stop for this part.